So a little bit things that we left from last notebook is how we trained with gradient-based method. I think we have spent enough time on this, on stochastic gradient descent with the mini batch gradient descent. This is just a simply an application of what we did and on the neural networks. So what we actually had is, so this is just a simple revisit. So what we do is we initialize all the weight with the, like WL and the BL here. So this is my theta, which is the parameter that I want to learn. What we do is we first randomly shuffle this training data set for all the training samples, xi and yi. So first thing that we do is we're using the backward propagation we just mentioned about to calculate all these partial derivative of Ci with respect to theta. So theta is WL and BL for all the L's, right? Then what we do is you update the weight and bias using the the learning rate given as below right here. So you have theta being updated. So if you go through the whole like training data set once, this actually and complete one epoch in the training process, then you keep repeating and the whole like process until it converges. Right. So this is stochastic gradient descent. So the key point of stochastic gradient descent is you only need to calculate and a CI one by one. You just kind of calculate CI, you update like and according to that, and update the parameter according to it. The second one is mini batch. So basically, it's basically the same thing, but the difference is we randomly partition this remaining like data set D into M different batches, B1 to BM with a size of B. So the total M batches that we have is N over B with upper bound that we have. So because like sometimes it doesn't like have the right and it's like divisible. So that's we put and put back into the integer here. So basically just simply partition into like M batches. Usually this is like batch size is like 8, 16. And usually 2 to the K power. And everything else is just being the same. The difference is here is we instead of we use the gradient Ci and a partial Ci partial theta as the gradient. Actually, we use the like gradient of the loss functions with the restrict to the batch of Bj right here. So this is basically approximated by the summation of and a batch of B and a gradient of the sum with respect to the batch B and divided by B here. So this will be an approximate of the gradient of the loss functions by the batches B and BS. So this actually is and will be the an approximation of the gradient. All right, so this right here, and we're going to continue to update the weight and the biases using the learning rate right here, as we mentioned and previously. So this actually complete. And again, like if you go through this in a training data set once, this actually complete one epoch. It will like we can continue and it is like and epochs until it converges. So here what I'm saying that epoch meaning the neural network and they use like all the training and data for one cycle. In one epoch, we use all the data exactly once. For each complete epoch, we have several iterations. This iteration is number of batches. All the steps is through all like random partition training data to complete one epoch. If you are like in a mini batch right here, this actually has M batches, so that would be like M iterations. If you are, working with stochastic gradient descent, that will be N like iteration because we're updating the theta for each of like the I. All right, so and also the choice of learning rate is crucial here. Usually we choose the constant learning rate to start with, but you can just like gradually decay this learning rate if needed. Okay. But there's also a problem with mini batch and a simple stochastic gradient descent. It's sometimes very hard to like navigating the ravines, which is like under this surface curve is and much steeper in one like dimension than the other. So basically, it's like super steep. It's very hard to like climb out. But like as once you climb out, there will be like even like a deeper well that 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 you can like explore. So I mean to help this an optimization and a scheme to climb out this well, and what we can do is we can introduce something called momentum term. So this is basically this I want and what I'm going to do is this is SGD oscillate and across the slope of the this like ravine, while only making like and a little bit like and progress along the bottom toward to the local optimal. So this is like some kind of like in a situation that you have like, and you can see this. I mean, so in this direction, then that would be the direction that you should go. But this is like super narrowed and the domain. So that's why if we choose the gradient descent, it was just doing zigzag and going around. So that's why they will be like quite slow to and to converge. On the other hand, if we have a momentum, so I mean this momentum here is I'm going to use the past and the and not only with the like and the derivatives at this point I want to like and introduce and like passing through I mean the gradient in the past. So I mean you can think about this is I'm using the autoregressive an argument to use the like previous like and a gradient and weighted like gradient and I mean into the update. So here and usually and this momentum is set to be like 0.9. If we have this like momentum, it will usually like and accelerate the standard SGD and converge much faster. And this whole thing is pretty like simple to like implement. It's just like and the average of the gradient here. This whole idea comes from like and the physics from like I mean it's a very commonly used method. I mean just in case of this kind of weight updating, we can think about this weight as like particle traveling through this parameter space. Then like and occurs like an acceleration and from the gradient of the loss. So this is a very common trick that we trying to work out to accelerate the the optimization process, and we can try different and the momentum and the techniques. So this is like in a slightly different version that it's called like and then like Nesterov and the momentum. So this basically momentum and update is just being like an update at a different theta here. So here we're just using and the theta equal to theta t minus 1. Here it's just and use like the most updated theta right here. So this theta is I mean so an update at this point. Okay, so I mean just using like and a slightly different and a version of momentum. And it turns out this and with like different and methods of, and whether using like momentum or like Nesterov and momentum, and sometimes like one is faster and sometimes the other is faster. You can try like both of that to see like which one is like performs better. But in general, and SGD with the momentum is, I mean, what performs with well performs better than the SGD without the momentum. So as you can see right here, so right here it's usually being trapped in this like and a narrowed domain. On the other hand, this is being like and can move much faster here. All right, so this is what we left. This is pretty straightforward. I want to actually implement everything from scratch in deep neural network. So in the deep neural network, so basically we need to define this network with this model structure. So basically the key is the model structure has the, I mean the model structure has the and input features has number of the hidden layers, activation function, and the cost function, and so on. So, and the whole idea is very simple. It's that after we define and structure, and that means we specify what kind of the like we fixed an architecture of my neural network. Then what we do is we're going to initialize this model parameters. I mean this model parameters is my WL and BL, and we were going to talk about so this initialization and it's a little bit later. Then we're going to loop until converge with these three little steps. The first step is forward propagation, basically to calculate all these AL from 1 to the capital L. So this is, and then by the end, we are going to calculate the current loss for one single point, for one single sample point. Then we're going to do calculate the gradient by using the backward propagation, and which is my delta L. So this is and both of that. Then with the gradient, we are going to update the parameter by using stochastic gradient descent here. All right, so that's kind of the whole idea that we want to do. So we actually want to implement everything from scratch, just using NumPy and SciPys. So the first thing is we are going to define all these activation functions and the cost functions. So right here, this is my activation function. So this is nothing but sigmoid, and also that would be the derivative. So basically, it depends on whether you want to passing this argument of the derivative equal to true or not. If it is like derivative equal to true, it will return the derivative evaluate at a z. If not, it will just return the function values. Same here for the square loss, for the register loss, and so on. And this is one hard encoding that I think you already and actually implement this in your homework. And the first thing that we do is we need to initialize this parameter. So, and what we do, and we know that will have like L different set of parameters. L is from 1 to the L and capital L. So what we're going to do is we're going to using Gaussian and Gaussian initializations of, and we know this and the dimension will be and the layer dimension of little l times like layer dimension of L minus 1. So this is basically the rows will be the current and the current numbers. The numbers of the current layer, and the columns will be the and the numbers of the previous layers. Here I'm going to put this times 1 over square root and root of and the layer dimension L minus 1, such that this is basically has the variance. It's basically the variance here is 1 over h over and h over L minus 1. Right, so this is basically so the variance of each like entry is as like 1 over and h L minus 1. So we're going to talk about this and the initializations and a little bit later. This B is so it's initialized with the Gaussian, just standard Gaussians here. So the first thing that we are going to input is forward propagation. So basically an output will be my A, right? So A will be my final layer output. And also need to install all these like AL minus 1 and ZL. So basically these are all intermediate values stored. Okay, so everything before applying. So that activation like functions. So A previous is input of the previous layer. We will loop through all the layers of the network. We'll compute this like linear transformations from 1 to the capital L. After that, we are going to take the value of Z and give it to the activation functions. This catch value are actually stored away that it can be accumulated as a list. So finally, so it will be returned as the output and the stored catch, right? So we have this and the like AL minus 1 and a ZL. So this like catch here is we're going to and like keep this A previous one that is the output from the previous layer, and the ZZ is the current, and the current and the like pre-activation values on the current layers. So this is A previous and Z. Right, so I mean, so you can go through this pretty straightforward, and all we need to do is just like loop through this and the linear layers and one by one. Okay, so and everything, I mean, so like, I mean, this catch is like and stored, I mean, in a dictionary, so you can just access this one by one. I mean, in a list. And also here, and for the backward propagation, we're going to create this kind of dictionary for mapping the gradient to each layer. So we basically loop through the model in like backward direction and compute the gradient. So that's, and I mean, the whole detail idea has been like talked about in the previous lectures. So it has all the an input. So you can see this input is quite complicated. AL is the I mean basically final layer and output. It's coming from the forward propagation. Y is one hot vector of the label. Catches is all these intermediate values stored because we need to use these informations. So what we have is just A and AL minus 1 and a ZL. So these are the information that we have. Okay, so these has like L from 1 to the L and big L and also and these parameters. So this parameter actually is installed as a like so it's actually stored as a dictionary. We have like W1 to and to WL, then we have a B1 to like BL. Loss function, so you can choose whatever loss you want. You can have a square loss, by default square loss, and you can have a log loss if you want. And activation function, here by default is sigmoid, but you can definitely write your softmax functions if you need it. Okay, the output will be a gradient. So basically the output will be the gradient of W1 to gradient of WL, and the gradient of B1 to gradient of BL. So these are all like the gradient information that we needed. All right, so let's just try to compare what we are and what shall we doing here. So we know this whole thing is at a forward and a forward propagation right here. It's already being done here, so the backward is basically we need to calculate this gradient and partial C partial AL. So that's why we need this information of AL and the G prime of ZL. So this is the delta L. Then we're going to using this delta L to loop through and to going backward to from L you get L minus 1 and so on. All right, so first thing first, we're going to create all these catches. So this is basically all these like gradient being like empty. The first thing that we need to calculate is the delta L. So this delta L is basically the first thing is we need to do the loss function, take derivative with respect to AL and evaluate at AL. So that would be the loss function of ALY, and we like and output is the derivative right here, and the same thing is activation functions and derivative of this activation functions evaluate at ZL. So this will be like that. So this is element-wise product. I only have this product term right here. Okay. So then we calculate this gradient, and then we calculate this gradient of dB, and then we calculate this and the dWL as well. So this is nothing but I think I already mentioned here. So this is this is basically delta L and times of AL minus 1 transpose. So we need to get AL and minus 1. It's coming from the catch L minus 1 right here. I believe this is giving you a row. So this is giving you a row. Yeah, this is giving you a row already. So that's why here you actually have to get a column here. So that's why you and put array dot t, that's a column here, columns and a dot a row that give you the matrix. So and at any time you have to make sure you are getting a matrix, right? So you are getting the gradient of the and the DWL. So this will be your delta periods. And which in this case is will be my delta L. So everything else you actually have to go through this whole iteration to calculate this delta and the delta little l here. So this is basically this WL plus 1 transpose dot delta L plus 1, then element-wise product of G prime. So right here, this will be basically W current, right? So I mean, this current one is for the L plus 1, and which is current one, then dot of the delta current, then times activation function, which is the and a sigma dot evaluate as Z current, and I require this to have a derivative here. So this is basically the key part and to calculate and the period and the next delta L from like backwards. So there are some things that you have to be a little bit careful, all these parameters, and you have to get the right and the right order and the right ones, and what is the right like W current, what is the right A periods, and what is right Z current. So you have to find the right index to extract the right and amount. So that takes a bit like effort to find the right index to work with. Okay, so and everything else will be the same. You get like gradient of dB, L plus 1, you get like and a gradient of dW, L plus 1. Okay, so you like go through these things and carefully. So you have the L minus 1 until 1. All right, so then we are going to, and once we have the gradient, we just simply and implement the SGD here. So we here we only like apply the SGD. So basically, this is the learning rate times the gradient on that point. Right. So this is fairly straightforward. So and we just loop through for all and all the parameters. So I mean since my parameter is B1 W1 to BL WL, so that would be 2L part of the parameter need to be looped through. So that's the main training function right here. We have X train, we have a Y train vector. So I mean, so my Y train is as a label. I need to turn this label into one-hot encodings that actually give you a vector right here. So right here, and also I need to specify the layer dimensions, learning rate, cost function, activation function. Okay. So basically right here, you have a parameter, you set up your parameters based on the layer dimension. So basically from here, it will specify what is your architecture of your neural network. In this case, it's just like how many number of neurons of these hidden layers, right? So maybe 4, maybe 8, and so on. And we are going to specify this cost and a cost and function with respect to the that epoch. And then we get this learning rate, and we reshuffle the index. That would be equivalent as we reshuffle the data at all as well. So what we do is we first do the step 1 to do forward propagations. We get the output of Y hat and it catches. Right. So this is just so we get all like necessary informations. So then we are going to actually use this cost functions to calculate the cost of I and add them up. This will be your y hat, will be your predictions, but your ground truth will be y train vector of j right here. So you're going to calculate the cost functions and add up to the cost of I. Okay, so this cost of I is the cost at ith epoch. Then from the backward propagation, you calculate all these gradient with respect to those 2L parameters, number of 2L's parameters. Then you update your parameters with the stochastic gradient descent. Okay, so at the end, you got the total cost, and what we want is average one, so we divide it by n. So you're going to output this cost right here. So you're going to, and after and one epoch is run and done, you are going to and print this out. Wait, why I'm getting this? Yeah. At epoch of I. Yeah. So like this is basically to run one epoch. That you go through all the indexes that you have. After one epoch is done, then you run this and calculate this and the cost, which is and the cost of I divided by n. All right. So at the end, you are going to and return your parameter and the cost bands with all the costs after each epochs. So this is the main function to train your neural network. And also this is prediction. So this is and your prediction functions. So so all we need to do the predictions, if you have a new data of X test, we go through one by one by doing the forward propagations. So we don't need to do any backward propagation on test the data set because we are not trying to train any and perform training on the testing data set. We only need to make the prediction to do the forward propagations. We only need and they need to get the y hat, which is the output of the last layer. So then the label of the prediction will just be the argmax of y hat, which corresponding the index give you the maximum predicted probabilities. All right, so that would be and that would be so the label that you want to be predictions and predicted. This is decision boundaries. This is something that and help us to do some plot. And here, and we're going to generate some data here. This data looks like this. It's clearly a 3 spiral here, and obviously cannot be separate with and the linear functions. So and obviously that's not really and straightforward or easy to separate. And in total we have 300 training data sets. So and each branch has 100 data point, and we have 150 testing data set and additional 150 data set. All right, so what we do is we start and to initialize this neural network. We start with a shallow neural network, just and we only have 32. So and the number of neurons for and for the input that would be fixed, which in this case is just being 2. Then and the number of classes that would be 3. These 2 parts cannot be changed. The only thing that we can change is 32, which is the number of the hidden neurons in the middle. The cost function will be square loss, and the activation function will be sigmoid. Okay, so here I'm just and you can try constant learning right here. We're trying some power law decays, and that would be and I'm running 100 epochs. I'm training this and the data is with X strings, Y train vector. I think I did this Y train vector right here. just to ensure this turning into one hot vectors for each classes. All right, 100 epochs, shallow neural network, 2, 32, and 3. You have all these informations. You can see after each epoch, the cost start to decreases gradually. Eventually, after 100 epochs, the loss is about 0.0155, which is quite loss and quite small. But if you actually do it for and the logistic loss, and you can try with the the logistic loss here. So only thing that you need to change is this like cost functions into and the logistic loss, and everything else will be the same. So like if you do this, you can see this and the loss drop pretty quickly from 2.08 until like 0.005. Okay, so you can test with all these and testing data set with the two different and loss, and for this way that what we can do is we can make predictions of parameter square on the testing data set and the parameter log on the X and the testing data set. So then we are going to compare with the error here. So you can see for the square loss, we're getting about 1% of testing error. For the logistic loss, we're getting like no error at all. It's 100% accuracy. I'm accurate. So let's actually plot this and like decision boundaries. If we choose the square loss, you can see this is the decision boundaries on 2D. And what does that actually look like? And you can see from training data, we still have some point being classified wrong. So this is it's 1 point here, another point here. That we still have some error here. But you can think about if we're using square loss, this is more like piecewise quadratic functions that we want to piece things together. If we're using the logistic loss, this is more like and the less smooth. Right here, you can see we have like more rigid and turns right here. But in terms of logistic loss after 100 iterations, it can perfectly separate these 300 points into like 3 different classes. So these will be your boundary, and decisions. And you can see it can separate these and hold 2D spaces almost perfectly, I would say. All right. So so actually we want to plot everything as well, so we can see so we can plot the cost function at each epoch, but everything will be in loss and the log scale. So you can see and for the square loss, it actually like decreased quite slowly, and you can see there's like and the region right here, it just it decay almost and the significance slow and gradually, it's almost like linear in log scale. On the other hand, if we choose the logistic loss and the log loss, you can see in this region, it decreased significant fast, right? And much faster than square loss right here. And after like 20 or 30 and the epochs, it start to decay slowly again. But the beauty here is if we turns out and to choose the square and the logistic loss and the log loss, and it turns out it can converge faster compared to the square loss. Why? Obviously that's a very interesting question. Why somehow the log loss can perform better than the square loss by just change the loss function here. This is because of the following thing. Let me just go back to the notebook. This is because of if we get this square loss, we have partial Ci, partial WL, which is the derivative of my last layer. This is equal to AL minus YI element-wise product of G prime of ZL dot AL minus 1 transpose. Right? If G here, we use the sigmoid, right? Is sigmoid. So G prime of ZL will be approximately equal to 0 if ZL is large. So that means if this thing is like n equal to 0, then the gradient will be small. So that means my WL will learn very slowly. But in logistic loss, this partial Ci, partial WL, and what we got is actually, I think it's logistic loss. Logistic loss. I think this logistic loss, if we're using logistic loss, okay, let's go back to the formula of the logistic loss. Just want to make sure I got it right. Logistic loss. I see. So, I mean, for the logistic loss, we have and a partial Ci, partial AL is actually equal to, if it is derivative, that would be AL minus YI and divided by AL times 1 minus AL. It just happened to be the denominator here will be AL minus YI, and that will be just precisely equal to Z prime and a sigma prime of ZL. So everything just cancels out because we have, and that would be just AL divided by sigma prime of ZL times sigma prime of ZL and 8L minus 1 transpose. So basically these two things just cancels out. What we actually left is AL minus YL L minus 1 transpose. All right. So you can see this actually, the G prime term is missing. And we no longer have, this G and a sigma and the sigma prime terms. So like this term is missing, right? So this term is gone. So this can have large gradient. Even sigma prime ZL is large, is small. And just because, this small term is got cancelled from the log loss and from the derivative of the log loss with respect to AL. So that's why, this gradient descent will move faster. Even this AL is far away from YI. So which is quite ideal in this like situations. Okay. There are a lot of other things that you can work through. For example, the neural, and this is what we're trying to work out right here. And I would suggest you to actually implement this and by yourself. And here, this neural network, and usually like to overfit, especially those like insufficient training data. And we have like huge amount of parameters. So it's very natural it will overfit because and the number of parameters is so large. And of course, we can add some like the regularization terms and the form of lambda times of the p norm of W here to the cost functions in order to prevent any kind of overfittings. And we can do L1, L2 regularizations of Frobenius norm of this W. And sometimes the Frobenius norm is also very popular here. You can actually implement this by yourself. It's not very hard to do. And also this initialize weight and bias, we have talked about this. I mentioned this biases for all the neurons are initialized as standard Gaussian random variables. And for this weight WL, if we like initialize this Gaussian random variables with a mean 0 and a standard deviation, 1 over square root of HL minus 1. This HL minus 1 is the number of input weights to these neurons. So this is, this H is like a numbers of the neurons at layer L minus 1. The reason that we want to do it is I want this total input of ZL has small standard deviation around 0, so that if my ZL is like close to 0, then this neuron will start at the middle, not from two end. If your ZL is starting from two end, then this like G prime at ZL will be very small, and then this neuron will be saturated. This is very bad, will create this gradient vanishing problem. But if we choose this kind of initialization, this can ensure this ZL has like small fluctuation around 0, and then this like G prime of Z and Z0 will be maximized at this point. However, you cannot just set all the BL and the WL to be 0. This is a bad as well. But why I'm not going to talk about this in this course, we were going to discuss that and analyze it in 593, right? So there are more to be discussed in the practical machine learning part. Okay, so and also, how do we tune this hyperparameters? There are a lot of hyperparameters need to be set up. For example, how many numbers of and how many and hidden layers and how many and neurons in each hidden layers, and what kind of activation function shall we choose? What kind of loss function shall we choose, and so on. And what you can do is you start with a subset of data, small network, and for example, you just train 784 by 10. This is nothing but an logistic regression. So there will be no hidden layers. And then you try one hidden layer with 32. And that's a good choice to start with. Then what you do is you monitor this validation accuracy. And after maybe 1,000 training, after every 1,000 training data set. So you play with these parameters to get a quick feedback from this experiment. It's very important that you only start with a subset of data. If you directly work on full data set, that will be way too expensive to work with. Once things to get improved, you can vary each hyperparameter separately while fixing the rest. You can do grid search, you can do random search until you see these results start and stop and improving. So so you can using and a grid search, random search techniques to find the best options of the hyperparameters. And also we can and here we're just using sigmoid functions throughout all the layer, include the up and output layers. Right now, what you can do is you can using ReLU as well. You can modify your code to use ReLU. I didn't actually implement that, so you can use ReLU in these hidden neuron layers and sigmoid in the output layers, and compare the performances. And also you can implement with an SGD with the momentum, and to see whether it actually speed up the program and the process or not. All right, so let's see what we are trying to do here. So this is something to have a brief mention about what actually happened in neural network. So if we just trying to create a significant larger boundary here, so see we don't have the data right here. So this boundary is just naturally extended out, right? So you can see this boundary just naturally extended out. Doesn't have this perfect idea of how to spread up and spiral out with the data. But of course, if you trying to shrink things a little bit, and you can see this is being and perfectly separate these three branches up to a certain point, they start to and they don't know the data, they start to and stop and giving you any reasonable end result. For the square loss, it will be almost straight line to extend it out. For the log and the log loss, that's still it's not very smooth and spreading out. You can see this is going a little bit unsmooth here. So, and what we can do is we try and understand what is neural network doing, right? So, the way we do is I'm going to insert one more hidden layer with only two neurons, right? And two hidden neurons. The reason that we add these two hidden neurons is because if we only have two hidden neurons, that we can visualize it, right? So with that, we retrain everything with a square loss. You can see this whole thing start to decreases, which is good. And what we do is I'm going to get this forward propagations, but I'm going to get information of catch 2. That means it's it's everything of output after this two neurons, right? So and before this and output layers, and after this and the last like and hidden neurons with only 2 neurons. And because we only have 2 neurons, we can actually visualize it. So what we do is we actually visualize this data right here. So it's basically what it's doing is previously these data are not linearly separable, right? So these are like 3 branches, obviously, and they are nonlinearly separable. But right here, if we trying to create this data like this way, it's more like to be linearly separable right here, because this is just and to be spread out in these 2D spaces, and there's a possibility you can draw a line to separate these 3 classes almost perfectly. Okay, so that's exactly what is done. You can even try all the points on the spaces to make a prediction for the yellow, green, and black. So this is all the point for the whole phase spaces to make the prediction. So basically, you can see there's almost a straight line here, and almost straight line here, and almost straight line here to separate the whole space in 2D. That's exactly the whole idea of the SVM, but it's being reflected in the neural network. So what neural network is doing here is, since I created like hidden layer of 32, so that means it's it was initially just 2-dimensional in a data set. And what we do is we map into much higher dimensions. I'm on the 32 dimensions. And I hope once we map onto the 32 dimensions, these data will be linearly separable. Right? So so after the and the 32 and the last layers and the second last layers to the output layers, this will be nothing but a simple and the logistic regressions, right? Or multi-class and the logistic regressions. If before that everything is being linearly separable, then we can just simply apply the logistic regressions. We can just solve that and to find out the linear separate part to separate these data in high dimensions. So this is exactly what is doing in the neural network. So that we map into much higher dimensions and trying to find out linear separator or decision boundaries in higher dimensions to separate these and the classes. Okay, so that's why this whole thing will be very successful. And it basically has the philosophy of that. SVM. But however, the problem of an SVM, as we talk about, is really expensive to run. But neural network, we have a lot of good techniques with the stochastic gradient descent, with various interesting ways to optimize this loss functions, and this loss function is usually tailored to this networks very well, tailors to this activation function very well. This whole thing becomes more like generalized version of the SVM. It's much generalized than the supported vector machines. Okay, so this is and you can think about SVM as being a special cases of a simple deep neural network. Right. All right, so that's everything I want to talk about on the neural network. So I think in homework you're going to work through all these details right here. And you can see this implementation is not very hard. It's just maybe less than 100 lines. You can actually implement the neural network from scratch, which is quite interesting and quite and will be quite helpful for you to understand these materials. And you can test it out and try that out by yourself. All right, that's all.